The last topic for this section is piecewise functions, which are, as the name indicates, functions that are in pieces. Before we get to one of those, let's do a couple of simpler graphs first. So first let's graph f of x equals minus x plus 2. And I'll just remind you that f of x is just a fancy way of saying y, so this is saying graph y equals negative x plus 2. That's in the form y equals mx plus b. So we can see that this is a straight line with y-intercept 2 and slope negative 1. So it's going to go down 1 for every one it goes to the right. Next, let's graph g of x equals 3. Again, g of x is just a fancy way of saying y. So this is asking for the line whose y-coordinate is always 3. Like that. Now we'll get to a piecewise function. This is saying h of x equals negative x plus 2 if x is less than 1, and 3 if x is greater than or equal to 1. In other words, we're going to graph the line y equals minus x plus 2 when x is less than 1. So there's a changeover point that's happening here at x equals 1. We'll start by graphing the line that we just graphed, except we only graph it up to x equals 1. So that's this line to the left of 1. Then we're supposed to do the graph of y equals 3, but only when x is greater than or equal to 1. So in other words, only to the right of 1. So that's going to look like that. Now, one modification we need to make here, this dot on the slanted line, that's got to have an open circle at the 1, because we are not actually including the point where x equals 1, because this piece of the graph is only for x less than 1. Not including 1, whereas the other piece of the graph includes x equals 1. So we have a closed dot at 1 on that part of the graph. So this graph is in pieces, and that's why it needs two formulas to describe it. Let's try another one. Let's graph f of x equals x squared if x is less than or equal to 0. So that's the familiar old x squared parabola. Looks like that. Notice I've got a closed dot at x equals 0 because this first piece of the graph includes x equals 0. It's x less than or equal to 0. The other piece is the 1 over x graph, which hopefully you're familiar with as well. That looks like something like this. And this graph actually has a vertical asymptote at x equals 0. So that piece of the graph never touches x equals 0. So I'm not going to need an open dot there because there's no dot at x equals 0 for the 1 over x graph. Here's another one. Write as a piecewise function and graph g of x equals the absolute value of x. Again, this should be a familiar graph for us. The absolute value of x graph is this V shape. But what's this business about writing it as a piecewise function? Well, one of the ways of describing absolute value is to say if x is greater than or equal to 0, in other words, if the thing inside the absolute values is greater than or equal to 0, then the function output is just whatever was inside the absolute value bars. Whereas if the thing in the absolute value bars is negative, then the output is the opposite of that. And notice that indeed our absolute value graph, the left side is the line y equals negative x, and the right side is the line y equals x. Now you might wonder, if we already know what the graph of the absolute value of x looks like, why write it as a piecewise function? Well, it turns out there's things we're going to do to functions in calculus that just can't be done to absolute value functions. And the only way to deal with absolute value functions is to turn them into piecewise functions. So let's see one more example of doing that. Let's write h of x equals the absolute value of 3x minus 6 as a piecewise function, and then we'll graph it. So h of x will be, well, if 3x minus 6 is positive or greater or equal to 0, so if 3x minus 6 is greater than or equal to 0, then its absolute value is just itself. Whereas if 3x minus 6 is negative, then its absolute value is the opposite of itself. Now, we can do some cleanup here to make this more user-friendly. So notice that notice that the changeover point for the two pieces is when 3x minus 6 equals 0. In other words, when 3x equals 6 or x equals 2. That's the changeover point. So another way of writing those ifs is if x is less than 2 and if x is greater than or equal to 2. That's going to help us graph because, again, we need to know where this changeover point is, which is going to be at x equals 2. And then the piece where x is greater than or equal to 2, the output's just going to be 3x minus 6. The piece where x is less than 2, which makes 3x minus 6 less than 0, is going to be, I'm going to distribute that minus sign in, minus 3x plus 6. So what does minus 3x plus 6 look like? Well, that's a straight line with y-intercept 6. 1, 2, 3, 4, 5. Whoops, I needed a little more height there, but we'll just put a dot up there at about 6. And slope negative 3. So it's going to go down 3 for every 1 it goes over. Down 3 for every 1 it goes over. Now, before we go on, can you see a modification that I should make to the line we just drew? That 3x minus 6 line, that minus 3x plus 6 line is only graphed for x less than 2, not for x equals 2. So I actually need an open circle there to indicate that dot is not part of our graph. Then for x greater than or equal to 2, we're going to graph 3x minus 6. And I think I'm going to just do a little xy table for that. I think that would be the easiest way to do this. This piece uses x equals 2. So I'm going to have 2, 0. So this dot's actually now going to get filled in because there's a dot right there from the other piece. And then how about we graph x equals 4, so that's 12 minus 6, which is 6. So up there.